Hey Algebra 2 students, hope you guys are doing well. I miss seeing you guys every day and hanging out with you guys. We are on day 4, which is Arithmetic Series, which is a fancy term for sum. So our previous lesson was just an arithmetic sequence of numbers. We're going to look at what happens when we add them together. Okay, so the first thing we've got is our math meme of the day. So I think this one's pretty funny, and it's a good throwback to when we were dividing polynomials. And remember, we did long division in the sense that I showed you guys an example, and then I showed you the trick of how to do synthetic division to make it easier to divide polynomials. So when you are doing your long division problem in Algebra 2 and get a remainder, you are not the factor. This is a nice little wink to the Maury show, where they do paternity tests, so you are not the father. Crowd cheers. Just thought that was kind of a nice wink to an old topic. So to start us off, before we get into the new content, I just wanted to do a quick warm-up just to refresh our minds of what an arithmetic sequence of numbers looks like. So you've got two warm-up problems. The first one gives you a sequence and asks, is it? And if so, to write that explicit formula that gives you any term. Part B asks you to write an explicit formula given a couple of clues. And we are assuming for Part B that it is arithmetic. Okay, so the big thing with Part A was I kind of ended the first video on arithmetic sequences with the point that you can't assume that any sequence is arithmetic. You have to be able to deduce that it's arithmetic based on finding that common difference between all your terms. Okay, so take a quick sec, pause the video, and work out the warm-ups to see how you're feeling with the older content. Okay, so here are your answers for the warm-up, just to do a quick double check with how you're feeling on just basic arithmetic sequences before we move on to our new content. For Part A, it is arithmetic. You can tell because when you go from one term to the next term, there is a common difference every time. In this case, we are subtracting 4 every time. Remember, you can add or subtract to get to subsequent terms. Either way works. And then I put the general formula here, and I labeled each part. So you've got your first term, your common difference, and n minus 1. Remember, the reason why we have the n minus 1 was because a lot of people at first think it's more like this, like 10 minus 4 times n. However, if I were to plug in for the first term, plug in a 1, 10 minus 4 times 1, that would give me 10 minus 4, which would give me my second term, and I really want my first term. So the key is we don't want to be subtracting 4 until we move on to term 2. So in order to make that that 1 turn into a 0, we make it n minus 1, because then 1 minus 1 would create a 0 and not have subtracting a 4. You can also think about it that from your first term on, you are going to be doing minus 4, and the amount of times you do the minus 4 is 1 less than how many terms you have, because you always start with the first term and then start doing your common difference after first term. So that's another way you can think through it. Part B, we were assuming it was arithmetic, and I gave you a couple of clues. The common difference, you can plug it in, and from there, the only thing you're missing in your general explicit formula is what your first term is. So I kind of did my first term work over here, and what I was thinking through is I wrote out term 1, term 2, term 3, using the notation A1, A2, A3, and I knew that if I knew the third term, I could go backwards, and instead of adding 12, because remember, if we go from our first term, assuming it's 196 to the next term, I add 12, right? So I'm trying to just go backwards is all. So if I subtract 12 twice, I can get to what my first term was. So you can do it that way, right? You can also think about it like if it were bigger amounts, like if it wasn't the third term, but like the 70th term, right? You could similarly say, okay, from the third term, subtract the first term, right? You've got 2, and that can kind of help you think through how many common differences there are there. Okay, moving forward, I've got just 1 or 2 quick practice problems to review our old content as we move on. So just a quick practice, I believe this is the first sequence that we were looking at, which we determined was arithmetic. And we already wrote it out with that beautiful arithmetic formula that allows you to plug in and find any term number. Just a quick refresher, we also had a vocabulary word called a recursive formula, which remember we used for our Fibonacci sequence. And remember that was where you add the previous two terms to get your next one. So like the nth term equals the n minus 1 term, the one before it, plus 2 before that, so n take away 2. So remember that was why the Fibonacci sequence was really why recursive formulas are useful and interesting. They're annoying because you have to know previous terms to get next terms. If we wanted to write a general rule for this one, we would say, okay, if I want the next term, like 6, remember this one had that common difference of minus 4, I take, this is called my next term, I take my previous term, and I do subtract 4, right? That's the general rule. Now to think through what the previous term would be called, if I call this a sub n, one bigger than a sub n would be one term higher, so the term number plus 1. And one lower would be the term number take away 1. That's kind of like if I do like the 5th term, the 6th term would be the 5 plus 1 to get 6. And a previous term would be 4. I would take the term number 5, take away 1, and get a 4. So I would call the previous term a sub n take away 1, term number 1 less. You can write it like this. You could also write it in another way, like a sub n plus 1 being your next term. Your previous term would just be a sub n. Both of these are the same. They're just writing it in two different ways, kind of using this thought process of what would be next based on where you currently are. Okay? And then another thing we talked about previously was sigma notation, right? This is your sigma notation. So this tells you where to start. We're starting at the 10th term, and we are going all the way until the 205th term because we are really, really into doing math. And here is your general rule. Okay, so go ahead and calculate this term. Make sure you write out all your steps. Did you ask yourself why Miss Goldenberg would ever make you think about that? You should be right, because, oh my goodness, you don't want to? Surprising. So here's where I'm going to tell you a nice little shortcut for how to add numbers. So we're going to do a quick story time to talk through how to add a lot of terms. Now, Johann Gauss is a famous mathematician, and there's this story about him that when he was in school, he was messing around and his teacher decided to punish him. And his teacher told him, go over there and I want you to add 1 through 100 and tell me what the sum is. And the teacher was really, really happy because they thought that they had saved themselves, hours of time before little Gauss was going to be done. And Gauss came very, very quickly and said, okay, I'm done. What next? So the question was, how did he add the numbers so quickly? And there's an interesting pattern here. Go ahead and pause the video and see if you notice any interesting patterns going on. Now, what a lot of students notice is that if you add the first and the last number and so on, kind of making pairs, you end up getting 101 every time, which is kind of interesting. So there is 101, and there are how many pairs, right? You want to think about how many pairs. So I'm going to write it out. So blank pairs of 101. And if you think about it, there are 100 numbers, right? If you cut that in half, there's going to be 50 pairs of 101. Okay, so you might say, okay, well, I could do like 50 times 101. And you would be completely right. So it's an interesting way to make the work simpler. It ends up being just 50/50 or 5050. And it's really interesting how that works. And the key thing here is just that we're making pairs, right? Now, the question is how to generalize that, right? So we took however many numbers we were and cut it in half, right? Numbers cut in half. So if we wanted to write a general rule, and on the next page I'm going to have like the formal note sheet, so no worries. So if I wanted to write a general rule, if I have n terms and divide it in half. That would give me that piece of finding the sum. Okay, and then how did I get 101? What did I do to get that? I took the first term and the last term and I added them together. So talking about what 101 represents, that's your first term, like a sub 1. And if we call the last term a sub n, this would be your sum. So a lot of people really like the arithmetic series formula. It's really intuitive for a lot of students. Some students have a little bit more trouble grasping it, depending on like your personal math brain, I guess. But generally, a lot of my students really like this one, and they're like, oh, okay, yeah, I can see that. That makes sense. So generally, students like this formula more so than other formulas we do in this chapter. So day 4, arithmetic series sum. So here's your beautiful formula, all nice and written out. And it's just the one that we found before. And I wrote out with your formula what each of the parts represent. And just remember that this piece is the sum of n terms, right? Depending on how many terms I ask you to add up. What we've got for the rest of the notes is I've just got, I think, four problems that are regular and one word problem that I thought was kind of interesting. So let's look at the first one. The first one says, use your arithmetic sum formula to evaluate. Now remember, this is your sigma notation, so this is where we start, this is where we end, and this is your rule. So I'm starting with term 1, and it just says the rule is term number, so it's 1, plus term 2, 2, plus 3, plus dot, 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 dot. And I want to go all the way to the 100th term. That's like 98, 99, 100. Does that look a little familiar? We've already solved this problem. This is your Gauss problem, the one that we just did. So remember, if we plug it into the formula, the sum of the first 100 terms equals how many we have? 100 into pairs, right? That's going to give us the 50 pairs. First term was a 1, last term was 100. Okay, so it should be 50 times 101, which we already found was 50, 50. Okay, so just a quick check to see if you recognize that that's the same thing. It's just written in a different way, right? So being comfortable with seeing the same question written in different capacities is an important tool in this unit, because I could give it to you in sigma notation, or I could just write it out like this. Okay, so just make sure that you're comfortable seeing it in both ways. This one is a different rule, right? We've got a new rule. If you want to think about like your general rule like this, and notice it's written in the general notation, right? It's got the n-1. Once in a while, they'll give you something that is not the actual arithmetic sequence, and you'll have to write out the first couple numbers before you see the rule. But this is written in the general formula. Okay, so we've got our rule. We know that we have to do the 10th term to the 205th term. Okay, so I'm going to find the 10th term, because that's like my first term per se. First term, that's my last term. So this one's different because it's not just the 10. You want to start with the 10th term. So it's going to be 10 take away, and 4 times 9 is going to give us 36, so it's going to be a negative 26. And then we also want to find our last term, which is going to be the 205th term. So 10 minus 4 times 205 take away 1 is 204. I'm going to real quick do this on my calculator. And it looks like it's negative 806. So we're now going to plug it in. And at this point, there's going to be something a little bit weird that's happening. So most of you guys at this point would say, okay, well, I need the number of terms. And you'd say 205 take away 10, which is 195. And you would say, okay, that's 195 terms that we're adding together. However, there's a weird thing that happens. There's actually 196 terms. And this is the problem that most of my students are like, oh my God, Miss Goldenberg, I don't even know how to count. And I'm like, it's okay. We're going to get through this. Now here's an easier example. If I do 10 through 20, so I listed out 10 through 20 down here, like 10, 11, 12, 13, and so on. when you count them, there's actually an extra term there, right? Past 10. There's actually 11 terms. And you would normally do 20 minus 10 equals 10 terms. But there's really 11